Purpose of this lesson is to look at this test called the comparison test. And this particular section is not, or this particular test is not that difficult, but what is difficult is the comparison itself. But I'll get into that after we look at the test itself. The comparison test says, if we have two series where they're positive terms, so we're not going to worry about negativity just yet. So we've got this particular series and that particular series based off of the sequences a sub k and b sub k. If we know that all the values of a sub k are going to be less than or equal to all the values of b sub k for all of the k in the positive integers, that is to say, this sequence is going to be smaller than that sequence, a sub k, b sub k, then we can say if the bigger sequence has a convergent series related to it, then the smaller sequence will also be will produce a convergent series. And then it also says if the larger sequence produces a divergent series, then if the smaller sequence produces a divergent series, then the larger sequence will also be divergent. So once again, if the sequence itself, one is bigger than the other, the convergence of the larger leads to the convergence of the smaller series. And the divergence of the smaller will conclude the divergence of the larger as well. So here again in this illustration we have two sequences, a sub k and b sub k, and here we can show that they're sequences, obviously, the discrete forms of functions, and just to prove that 1 over k squared is always larger than 1 over k squared plus 5 for all k's bigger than or equal to 1, I'm going to start with a little bit of logic. Notice that k squared is smaller than k squared plus 5. Then if we take the reciprocals, then 1 over k squared has to be larger than 1 over k squared, or x squared plus 5. So the idea here is when you reciprocate an inequality, you change the sign, you reverse the sign, because if 2 is less than 3, then 1/2, it happens to be greater than 1/3. So larger denominators in the end are going to produce smaller quotients. So when we're working with comparisons, what we'd like to do is we would like to take something we're trying to compare and find something that's just a little bigger than that. All we have to do is make the denominator smaller and the quotient will become bigger. Make the denominator larger and the quotient will become smaller. So I can always use graphical evidence to make sure that my comparison is valid, but the first thing you need to do is to verify that the sequences themselves are comparatively correct. Then we have the actual partial sum sequence that results from that particular series, and so here we can see the sequence of partial sums for the first series is larger than the sequence of partial sums for the second series. So if there is a limit or convergence for the small or larger series, then there's definitely convergence for the smaller one as well. So that's generally the rule in a nutshell. Again, the issue, of course, is going to be, what are we going to use to compare? The first thing to remember is the geometric series, that is exponential to k in this case, will always converge when the common ratio is less than 1. The other thing to remember is what we call p-series, and we're going to explore this further in later videos, but for now, what we're going to take is whenever p is bigger than 1, and this is careful to understand, whenever p is bigger than 1, then the p-series will in fact converge. So we're going to be able to use these facts along with these two other facts, and that is cosine functions are bounded by 1, and so stretches of cosine functions are bounded by the stretch factor. Same thing for the sines. So this is a useful tool for comparison as well. Anytime we see trigonometry, we can use 1 or -1 as a point of comparison, because it will always be the upper bound of the cosine function or sine function. So for now, we're limited, but we have any sort of geometric exponential decay functions. Those will be convergent series all the time. And then p-series, as long as p is not equal to 1, anything bigger than 1, then we'll be able to claim convergence as well. Again, all of this will be proven later. Well, this one was proved in an earlier video, but this will be proven later. But now we're going to use it. So that makes sort of the exercise here is what is it that we should be comparing to? It's a hard skill to master. In some cases it's really straightforward, in other cases it requires us to be a little thoughtful and contemplative. First case I already showed you or illustrated, we just compared to 1 over k squared. But in the second case we have the square root of k over k squared plus 1. So here's what I'm going to explore. We have the square root of k over k squared plus 1, and I'm going to make the denominator smaller, which makes the quotient bigger. So we already know that this right here has to be bigger than our given statement just by understanding algebra. And if we simplify this, k to the 1/2 over k to the 2, that becomes k to the 3/2, 1 over k to the 3/2. So that's what I'm going to use to compare here. Just again to confirm, first of all, we want to make sure that the sequences are in fact one larger than the other. So this orange one represents 1 over k to the 3/2, and the blue one represents the square root of k over k squared plus 1. And in fact, they do behave the way they should. And then we could also verify then that the sequence of partial sums are limited and in fact convergent, and that's just a visual to make sure that I'm arguing correctly. Here again, we have k minus 2 over k squared plus 3. These constants are fixed, and they're going to be insignificant as k approaches infinity. Therefore, we can simply relate this to k over k cubed, and k over k cubed reduces to 1 over k squared. Really straightforward. Now we get to the beast, 1 over k to the k power. I don't really know anything about k to the k kinds of functions. I'm sure it behaves a little weird or funky, but here's something I do know. Whenever k is bigger than 1, the k to the k power is going to be greater than or equal to 2 to the k power. You can see I had to say greater than 1 because when k is equal to 1, this is going to be 1 greater than 2, which is not true. So this is kind of inconvenient and it's not helping me. However, I will notice that if I choose 2 to the k minus 1, then when I let k equal 1, we're going to have 1 equals 1, so I can actually make a comparison. That is to say, in this specific case, for any k larger than 1, we're going to have k to the k be bigger than 2 to the k minus 1. Let's take k equal 10, for example. 10 to the 10th power will be bigger than 2 to the 9th power. I'm sure you would agree that's true. If this is true, then we reciprocate and change the inequality, and now we know that 1 over k to the k is always going to be smaller than 1 over 2 to the k minus 1, and that is a geometric decay situation. So first verify that the sequences themselves are in fact one greater than the other, and then verify that the partial sums converge graphically. So that's something that takes a lot of years of practice and insight and experience to know. That's why I'm telling you now, if you ever do see that. And also if you see factorials, you can substitute with whole numbers and use the less than and then reciprocate and change the inequality. That's going to be a strategy that could come in handy if you're trying to compare. Similarly, we get this one. This one is a little bit of a beast because it's hard to tell what to compare it to. But one of the things that I will observe is that we can make some statements about what if bases themselves were the same on the numerator and the denominator. In other words, what I did is I made this base one larger so that I know I have a larger numerator, and then I took this base and made it one smaller because this smaller denominator leads to larger numbers. So by making the numerator larger and the denominator smaller, I guarantee a larger number here. Cleaning up the expression, here we have 2 times 3 to the k over 4, or 2 times 4 to the k, which is 3/4 to the k. The 2's divide out, and the k's become the power on the entire quotient, power of a quotient. Therefore, the comparison here is going to be of 3/4 to the k power, which is, exponential decay, a geometric sequence. Therefore, we can find the sum. And lastly, we have the cosine squared of k over k squared. Notice the cosine squared, that's cosine goes from -1 to 1. If we square that, it's going to be bounded by 0 and 1 because there will be no more negativity. So we can just simply compare this to 1 over k squared and guarantee that this is larger every time. I hope you found that helpful. Thanks for watching.